Okay, good evening, everyone. Can you all hear me? All right, very good. Thank you very much. So today is our final lecture. So the semester is over, at least lecture-wise, and you have one assignment to go and also the exam coming up. We'll talk about that. So mostly today I want to talk about the one final topic on heap sort with linear time heap build. The algorithm and so on, and analysis. And also, I think your next test is going to cover questions on sorting heaps, mostly quick sort heaps and graph questions. And then we'll just go through a quick summary of the course. And also, I can say, time permitting, what the next steps are in terms of computer science major, that what you might encounter as you go into the next set of courses. Okay. So let's start again with building a heap by inserting elements one at a time. So we're going to build a max heap here. So let's do 34 first, and then we insert 2. It's a max heap right now. But when I get 45, I need to put 45 here, but then I need to move it, swap it with the move it up. If you have any questions as I go, you can type it into the chat room. All right, and then comes 7. So I will insert 7 here. 34, 2. Okay, so that's certainly not a heap. So I need to do some exchanges here. So that will be 7 and 2 and 34. Then comes 6. So 6 is going to go here, which is okay. It's still a max heap. And then comes 1. 1 is going to go here. So now we have a max heap. Okay, so if you really think about it, the number of operations, so if you look at how many swaps did we do in terms of inserting things. For example, we swapped 2 and 7, and that's and also 45 and 34. So we had 2 swaps, and then we did 6 insertions. 6 insertions. So in terms of counting operations, you can say we did 2 swaps and 6 insertions. Any questions there? Okay, so let's try to find the answer to these questions. So what is the worst case runtime for inserting an element to a heap with n elements? You can type the answers there for the 3 questions I have. So if you're inserting an element, a single element, it would be log n for inserting a single element. And the worst case to delete a max element from the max heap would also be log n, because once you delete the max element, you have to adjust the heap. Worst case time to find the max element, just finding it. So we're not trying to delete anything. That would be big O of 1. Okay. Now let's do a little bit of an analysis on what is involved in building a heap, inserting n items one at a time. So when you insert the first item, you just have to do, you only have to worry about going a log 1 distance. And if you have to shift it up, or you only have to do it log 1, because the 1 is the size of the heap initially. And then when you have 2 elements, the worst case is that the height would be log 2, so you would go up maybe 1 time at most. So when you have 2 elements, it's log 2. In other words, in general, if you have a heap with I elements, log I is the worst case operations you're going to be doing in terms of adjusting the heap to maintain the heap property. So if you do an exact count of how many it takes, so we are inserting n elements. The first one requires log 1 height traversal. Second one requires log 2 at most. And third one requires log 3. You might recognize log 2 and log 3 are pretty much the sort of in the same integer range. Any questions there? So that is the total number of operations. Okay, so these are the total number of operations to insert n items one at a time into a heap. Now, because we know the log of the product is the sum of the logs, so log of a b is log a plus log b, we can go backwards. So we have a sum of a log. Now we can write this as a log of a product. And the product here, 1 times 2 times 3 up to n, is in fact the n factorial. So now so how would you solve this? So we want to know what this is proportional to. We want to know what this is proportional to so we can find out the big O of this operation of inserting n items one at a time into a heap. So it turns out that there is a famous formula called Stirling's formula, which gives you an approximation to n factorial. It says that n factorial is approximately n over e to the power n and square root of 2 pi of n. So what we can do is we can take the log of both sides. So this means that log n factorial is approximately log n over e to the power n times square root of 2 pi n. I'm going to write the square root as 2 pi n to the 1/2. All right, so I'm doing a little bit of math here to understand the complexity of inserting n items one at a time into a heap. Now, this is the kind of thing that as a computer science major, you need to be able to do. So there's a little bit of math. In fact, this log formula that I mentioned here, log a times b equals log a plus log b, is quite useful in analysis. So the next step we can do is we have a product of logs. It's like log a times log b. So we can say that's equal to log. You can work it out in your piece of paper. So we have that plus the log of 2 pi n to the 1/2. So now, what can anyone suggest what we should do next? Okay, so take the exponent out. Very good. So let's take the exponent out. So we have log n over e. And then here we have 1/2 log 2 pi n. All right. Okay, and so we can write now. We can simplify further. We can just say this is going to be, I'm going to use another result that says log a over b is log a minus log b. That's also a useful result. So I'm going to write log n over e as log n minus log e, plus then I'm going to write this as 1/2 log 2 pi plus log n. All right. And so we have now simplified this formula using Stirling's formula to a place where we can actually say that this is big O of what? So it's the big O of n log n, because n log n is the largest term in this expression, and all the other terms, like there's an n log e, we can ignore that. Some constant term, there's a half log n term. They're all smaller than n log n. So therefore, we conclude that this is in fact n log n. So what we just proved is that the sum of the log 1 through log n is proportional to n log n. So that shows us that the inserting n elements to a heap one at a time is of complexity n log n. All right. And so once you have the heap built, let's see, I think the heap that we built was, I think we had 45, 34, and 2, and then 7 came here. And then we had 6, and then we had 1. I think that is the heap that we built before. Hold on. Well, let me see. 45, 7, 34, 2, 6, 1. Okay. So, yes, so you have to, I think question is, if you write big O of n factorial, how do you know it's n log n? I think you have to explain it like the way I did it. Okay, because we don't know what the log n factorial is. All right. So the heap sort is building a max heap and then delete elements one at a time and insert to the end. All right, so I'm going to do this right here in the heap itself. So typically what we do is we exchange the last item and the maximum item. So maximum item is 45. So I'm going to exchange the two of them. 45. Then you have 7, 2, 6. And now I need to bring down, now 45 is something that I will fix. I won't look at it. But 1 is not supposed to be there. And so what we need to do is you exchange 1 with the larger of the two to maintain, larger of the two means larger of 7 and 34, which happens to be 34. So now we have this. So now we have to delete the next largest element. Question: what do we exchange here? Which elements do we exchange to delete the largest element? Yes, so we would exchange 34 and 6. So we have 7, 1 here, 45 here is in the right place. And now the 34 came here, and 2 is still here. The reason I draw the boxes around them is to show that I'm not going to touch them. They're at the end of the array. Those are the elements at the end of the array. Okay, but 6 is not supposed to be there because 6 is smaller than 7, and so we are going to do a swap here with 6 and 7. Okay, in the next step, what are we going to do? What are we going to exchange? Seven and 2, correct. Okay, so we're going to exchange 7 and 2. So we're going to put the, let me just write a new one here. So we're going to put the 2 here, 6 and 1, and the 7 comes here, and then 34. and 45. Again, the boxes are the ones that are in the right place. Now, 2 is not supposed to be there because it's a max heap. So we need to exchange 2 with the larger of the 2, 6 and 1, and bring the 6 here. So the 2 is there. And the next step is going to be what elements do we exchange now? 2 and 6. So which elements do we exchange now? The next process. 6 and 1, correct. Okay. So we're going to be exchanging 6 and 1. And 2 is here. 7, 34, and 45. Okay, because now we have a heap which only has 1 and 2. And we have to swap 1 and 2 to make it a max heap. So the next exchange would be 2 and 1. So we will have 1 here and 2 here. Now 2 is final. Oops, hold on 1 second. Okay, so now if you look at the array representation of this is you do a level order traversal to get the array. So you have 1, 2, 6, 7, 34, and 45. All right, so that's heap sort. And you can perform heap sort using just the tree as I did right now, and then not worry about the array at all, and then translate, convert it back to the array. So essentially you are imagining doing heap operations, but you're really doing this in the array. You always, when you're sorting, you always have to do a max heap. If you're sorting in ascending order. If you're sorting in descending order, then you must do a min heap. Okay. So I mean, either ways, I think so the idea is that you take elements to the end of it. So whether this is an ascending order, so I did a max heap. For descending, min heap. So let me write it down. Ascending, you want a max heap. Descending, you want a min heap. Okay, so let's do an analysis of the heap sort the same way we did the other one. Remember that what we are doing with heap sort is we are deleting elements from the heap one at a time. Yes, so if we are told to, question here is if we are told to do ascending but told to do it with the min heap, yes. So you would just do it and then just reverse it. That's a linear time reversal of an array from ascending to descending or vice versa. So if you want to analyze this again, so we are saying, okay, we want to delete elements from the heap one at a time and put them into the end of the heap. As we know, the worst case deletion from a heap of size n is log n. And once you delete one, you're dealing with a heap of log n size n minus 1. So the next one would be log n minus 1. And the next one would be log n minus 2. eventually you come up with a heap of just one element, and the number of operations you have to do to delete is log 1, which is 0. So that means we don't have to do anything with a heap of 1, and that heap is in the right place. Now, what is the sum of this? So this is the sum of heap sort. This is the runtime of heap sort. Yes. So in fact, you should think about what we did before. Okay, I'd like you to think about what we did before in building a heap, inserting elements one at a time. I'm still not seeing the answer I'm looking for here. Yes, very good. I'm looking for this. So this is also log n factorial. It's given the other way. It's n times n minus 1 times up to n. But we showed that last time this is in fact equals to n log n. All right. So therefore, deleting elements from the heap at a 1 at a time is also n log n. So far we know that building is n log n. We proved that. And then delete is also n log n. And their sum is also n log n. So heap sort is n log n. The benefits of the heap sort, what are the benefits of the heap sort? What are the things that you can think about as benefits of the heap sort? Okay, no extra memory. That's good. So let's write the benefits of heap sort. No extra memory. You can do the sorting in place. It's guaranteed n log n time, which is very good. So we have n log n guaranteed. There's worst case, best case, all the cases are in log n. Anything else we can think of? So if you have a choice between heap sort and merge sort, which one would you pick, and why would you pick one over the other? Okay, merge sort is easier to implement, but what is the problem with the merge sort? Merge sort requires extra memory, that's true, as well as there's recursion overhead. And in this process, there's no recursion. This is purely an iterative program. All right. So there are some things that you want to consider because merge sort and heap sort are both n log n, but you want to consider one versus the other based on extra memory in the merge sort versus this one is. But so why would you use the merge sort? I think, yeah, okay, someone mentioned that it's stable. Okay, so heap sort is not stable. Okay, so heap sort is not stable. So that's one distinction between merge sort and heap sort. So if you ask why would you even consider merge sort, because merge sort is stable and heap sort is not. Otherwise, it seems to me that heap sort will always win in runtime over merge sort, but it's not stable. Okay. So here's the pseudocode for the heap sort. So we are creating whatever the new heap data structure. We insert elements one at a time, and then you delete one at a time and add it to the end of the array. Notice that the array starts from the last element, array.length -1. Okay. So that is sort of like a simple implementation of the heap sort, which is quite simple to do if you have the heap build code. Okay. So here's more. I'll put this on these lecture notes in the Sakai. So these are, I think these are probably the ones used in the book. So we have building a heap, which I'm going to talk about now in linear time, because so far what we know is that the build heap is n log n. But so how can you build a heap in linear time? The sorting is always going to be n log n, and the sorting is essentially this idea that sifting down, you delete the thing, this is the exchange part. So this is the exchange max and the last element. Notice that the last element is n minus 1. Okay, and the so this is really the heap sort, and this is the sift down, which is sort of going down one branch, swapping things, and adjusting it to be a heap. Okay, I'll put this code and you can take a look at it just to understand. Okay, next thing I want to talk about is how to build heap in linear time. Okay, so the big idea here is that we're building a heap in linear time. Okay, so it's clearly better than n log n, right? So we want linear time, which is less than n log n. So how do we do that? So let me show you the idea here. And then we do the analysis. Okay, so the idea here is, let's suppose that you're given this heap. So here's a heap, and the array looks like, I will go level order traversal and 2, 3, 0, 4, 9, 8, 7, 5, 6, 1. All right, so we have, that's the second level, and this is the, I guess you go by level 0, level 1, and level 2, level 3. All right, so we have 561 is in level 3, level 2, level 1. And the height of this tree is 3. It's a perfectly balanced tree. The height of the three T's. So the way that it's a complete array. And so what we're going to do is, here's the method of doing it. So we go through a process called Heapify. Okay, Heapifying means that you're going to start from the second to last. Okay, so the Heapify means start from nodes with at least one child. Okay, start with nodes with at least one child, and then make those nodes, you heapify those things. Okay, you see what that means. Okay, so what is the first node here with one child? At least one child. Anyone want to give me the answer? The first, take that tree, and what is the first node with at least one child? Okay, 9. Okay, someone said 9. That's true. I agree with that. So 9 is the first node with one child. Can someone tell me the index of 9? Because this is all in an array, right? So this is in an array called, let's say, A. So index of that 9 is going to be n over 2. That's correct. Someone said that, n over 2, right? So the index of 9, 0, 1, 2, 3, 4. Okay, that's the index of 9. And the array has 5, 6, 7, 8, 9. Okay, so that's the last index. So if I take 9, which is the index, and divide by 2, I get the index 4. So that's the integer division. Okay, therefore what we are looking at is n over 2 element. Okay, and what is the index of 4? So the index of 9 in general is, in fact, you can just say the n is the number of elements. There are 10 elements here. So you can just say it's n minus 1 over 2 if you want to, but it doesn't matter because the if you take n over 2, it'll give you the right thing. So the number 4 would be n over 2 minus 1, okay, because that's the one before that, right? That was the index before that. So what we mean by Heapify is that we try to make this part a heap. We try to make that a heap. The way we do that is we try to take 9 and see whether you can just make sure it's okay. You only have to compare here with 1. And because 9 is bigger than 1, we're not going to change anything. Okay, so the 9 and 1, and that's going to be fine. And all the other elements are in the right place. 0, 8, 7, 5, and 6, and then 4, and then 3 and 2. Okay, so we know that this is now a heap. Next, we look at 4 and try to heapify that. So what we mean by heapifying 4 is that we look at this part of the heap that contains 4, 5, and 6, and then try to make it a heap. How do you do that? What do you do to make that a max heap? Yes, you swap 4 and 6 because 6 is the larger of the two. So you're going to get 6 here, and then 5 and 4, and 9 and 1, 8 and 7. All right, so let me not write those things in because, all right, so that means I have heapified 9 and I have heapified 6. What's the next element to heapify? That's true, 0. Okay, because that's the one that comes next. We go in the order, the things that have at least one child. So if you heapify 0, what do we do? We have to do some changes, right? We swap 8 and 0. Very good. So we swap 8 and 0, and we have 7 here. Okay, now the 8 is heapified. And now next we're going to heapify 3. Okay, so that means we want to create a heap out of this branch here. So we have a 3 here. So what should we do with 3? So the question is, how do we heapify the branch with the root 3? Yeah, so we swap 3 and 9. Very good. So the 9 will come here. 3 is here. 1, 6, 5, 4, 8, 0, 7. All right. And now we know that that's a heap because 3, you have to move 3 down if you think that if 3 was smaller than 1, you have to move it down. So we have now heapified this branch, this branch, this branch, this branch. And one's left to do, which is a 2 here. Okay, so that's the final heap, which is going to be the entire thing. So in this case, what we need to do is we have to do number of swaps to bring the 2 down. So the first thing we would do is swap 2 and 9. So 9 goes there. So we know we are not going to touch this 8 branch. And 2 comes down, but then the 2 is bigger than 6 and 2 is smaller than 6 and 3. So we will swap with 6 and move the 2 there. And 2 is still smaller than 5. So I'm going to swap with 5 and move the 2 here. So 4, 3, and 1. So as you saw, the 2 came down. Oops, 1 second here. What happened? I made a mistake here. So it should be 5 here and 2 here. Okay. Yeah, heapifying can be min or max heap. In this case, I'm trying to make it a max heap. It's the same process as. Can you agree with the final heap that I have? I'm going to claim that this is a max heap. And I did the right thing. So in this case, 2 came down. Notice the 2 came down all the way to here, right? And 9, 6, and 5 moved up. And so 2 came down from top all the way to the bottom, right? Okay, now the analysis. All right, so let's do the analysis here. So I'm going to put an analysis like this. The things we heapified were elements 9, 4, 0, 3, 2. Okay, I want to know max operations I had to do to heapify each one of them. Okay, so you can think of operation as just a swap. So for 9, how many operations did I do? Someone said 2. I'm saying just think of a swap as 1. Okay, so I'm just going to claim it's 1. Okay, swap is really three operations, but I'm going to claim that to be 1. How about 4? 4 is also 1. Okay, so I brought down 1 through a branch. How about 0? 0 is also happened to be 1 because 0 didn't really come all the way down, right? It just came because that part of the tree is not complete. And if you look at 3, how many things did I do to bring 3 down? How many operations for 3? Yeah, I think it's 2, right? 2 operations, if I remember correctly. 2 operations or 1 operation? Maybe I just did 1, I think. Yeah, looks like 1. Yeah, we also have to check, which are the 2 big. In fact, the way you think about this is that it's true. If I look at the number of swaps, it's 1. Okay, but I'm trying to make a bigger point here. I'm just not counting these 2s and 1s. Okay, but the bigger point is that in the worst case, 3 would have come down 2 swaps. Okay, so it would have come down, in the worst case, the 3 would have come down twice, right? So 3 and 9, maybe 9 and 1, 3 and 1, if 1 happens to be bigger than 3. Okay, because we knew that 3 come down the branch of 9, but because 3 was bigger than 1, it stopped. So it's minimum 1, but max could be 2. Okay, so for 3, it could be max 2 swaps. Oops, messing up my writing here. Okay. Okay, for 2, how many swaps did I do for 2? Yeah, for 2, I did 3. Okay, so that's like the height of the tree. So we did 3 for the element 2. So if you add them up, it shows you how much it takes to build the heap. But in this case, it happens to be 7. It happens to be 7 operations here. It could have been 8, but it turned out to be 7. Okay, and this heap has 3, 7, and 10 elements, and so notice that the 7, the number of things that we did, is less than 10. Okay, it's less than 10, and 10 happens to be n. 10 happens to be the size of the number of elements in this heap, total elements in the heap. So it does seem like we can do heapifying operation for all the elements in linear time or less. Right? If you look at this, you might realize that we can do all the operations in linear time or less. Once again, 7 is the count I got, and then 10 is clearly bigger than 7. But how do we prove this? That's the next thing I want to do. I want to do the build heap analysis. All right, so some math is going to come up. Now let's, in other words, how do I show that build heap in this way is linear? So just bear with me. I'm going to show you some math here. So this is level 0, level 1, level 2, and level 4. I mean, let's say level 0, level 1, level 2, level 3, right? What is the number of elements in level 0 is 2 to the power 0, or max elements in level 0 is 2 to the 0. Okay, that's how many elements you have in level 0. In level 1, the max elements is 2 to the 1. That's equal to 2. In level 2, max elements is going to be 2 to the power 2. It's going to be 4. And in level 3, the max element would be 2 to the third, which would be 8. But in this case, we only have 3 because we are missing the other 5 elements, for example. Okay, they're not there. But the max would be 8. All right. So the height of this tree is 3. Height of the tree is 3. Okay. So here's how I'm going to do the analysis. Let's assume that this was a full tree. Okay, let's assume that this was a full tree. Has all the elements there. Now, when I heapify, note that I begin from the first element that has at least one child. So that means I'm only going to heapify from these elements here. Okay, so what I'm shading elements that I'm heapifying. So those are the elements that I need to heapify. So now let me ask a question. If you take, now if this is height h, this level is level, in terms of h, this is h minus 1 level, that's level 2. This is going to be h minus 2 and h minus 3 level. Okay, so because h is 3, they turn out to be level 0, level 1, and level 2. Now, if we take the elements in level h minus 1, how many swaps do you do max? For any element in level h minus 1, how many max swaps do you do? Only one, correct, okay? So because you only have to come down 1. So we will be doing, for elements in level h minus 1, we'll be doing one operations. But there are 2 to the h minus 1 elements in level h minus 1. Okay, if h is 3, there are 2 to the power 2 elements in level h minus 1. So the number of operations that you need to do in level h minus 1 is at most 2 to the h minus 1 times 1. For level, the previous level, there are 2 to the h minus 2 elements. And what is the maximum number of swaps that all of those elements will do? It's going to be 2, because all the elements in level h minus 2 will have to come down at most 2. Okay? And then level h minus 3, how many things that it needs to come down? So all the elements in level h minus 3, what is the most number of swaps you will do. Okay, 3. Right? So now the total operations is the sum of these. So I'm going to write it like a sum 2h minus 1 times 1, 2h minus 2, 2 minus 3 times. And that eventually I'll have. Notice that the 3, so I could write the last one could be 2h minus h times h. Right? When you have a 2, h minus 2, you got a 2. You multiply by a 2. When you have h minus 3, you multiply by 3. So that means this is 2 to the 0. The last one is 2 to the 0, which is one element. That is the root element that comes down at most h. Okay, so this is how we count the number of operations. Now, I hope some of you are familiar with this notation of writing a summation. So I'm going to write this as a summation of 2 to the h minus times I, where the I will start from 0 to h minus 1. Oh, sorry, h 0 to h. Okay, so I write that as a sum. This is something you have to get used to, this kind of notation. In discrete structures and other courses, you promote that this is means sum, where I goes from 0. So if I plug in I equals 0, you get the first term, I equals, well, actually, no, I equals, it should be I equals 1, right? I think I made a mistake here. Because if I equals 1, you will get h minus 1 times 1. If I equals 2, you will get h minus 2 times 2. If I equals 3, you will get h minus 3 times 3. If I equals h, which is the final term in the summation, you will get h minus h times h, which is what you see in the summation. Okay, now I'm going to take you to calculus. So in calculus, we learned that to find an integral, what we do is we take the integral is the area under the from, let's say, 0 to 1. What we usually do is we take these rectangles and add them up, and then we claim that it's the sum of the rectangle areas give you the area under the curve. Okay, there's a slight sort of a error in that because you're missing few things, but by keeping these things fairly small, like delta, very small, you can minimize that thing. So one of the tricks now, so the question is going to be, how would you ever find this sum? Because it seems so difficult to find this. It doesn't seem easy to compute this. It turns out that this can be approximated by an integral from 1 to h, 2 to the power h minus I times I, or we can call it x if you like, dx. All right, so what I did here was, this is a technique used by computer scientists, that a discrete sum is approximated by a continuous interval. Okay, notice the terms are the same, so it's the same idea that I have on the left-hand side. A discrete sum of these rectangles is equal to an integral or area under the curve. Do you have any questions there? So now I'm not going to do the calculus here, but the so obviously we can. Doesn't anyone remember how to integrate something like this? In fact, you can simplify this a little bit, like this. By the way, if you want to be a computer scientist, you have to deal with math. Otherwise, there's no other way to do it. Well, let me see. I'm going to write this again. Yeah, so I'm going to write this as 2 to the h over 2 to the x times x dx. And then I'll take the 2 to the h out because it's a constant. It doesn't depend on x. So I'll have 2 to the minus x times x. And someone said do integration by parts. That's correct. And if you do that, you will actually conclude that this is going to be of some function of n. Okay, and the relation between n and 2h, in fact, you will come up with the answer to be 2h, proportional to 2h. But 2h is the number of, I mean, roughly the number of elements in the tree. Okay, so this can be replaced by n. So that gives you the proof of that the building a heap by heapifying is linear time. Okay. Oops, I'm running out of battery, but hopefully I'll last enough. Okay, let's take like a 1 minute break. I'll be back with the my power cord. Okay, I'm back. All right, so let's continue. Can you still hear me? Okay, very good. There are a few exercises, but I don't think I have time to do them. I put them mostly as a way for you to practice for the exam that's coming up. So the first exam question is tracing the quicksort algorithm on an array using median of the first, middle, and last entries. Okay, I'll probably create a small video on these things, how the solution is done, rather than trying to do it right now. The second question is, given the input array, we want to trace the build heap algorithm on the array to build a max heap and also count the number of comparisons it did to build a heap. Okay, and also doing the heap sort after you do that. So I think some of these things you should try to practice as a way to prepare for the upcoming exam. And so here's another question where I again practice the shortest path algorithm. Maybe try to find all the shortest path from the node I to all the other nodes, and also find the shortest path tree. Okay, which means that there's a unique sort of a tree that gets built where I as the root of that tree. All right, now the shortest path Dijkstra's algorithm can be applied starting from any node. So let me ask you a question. The question is, the shortest path from, so if you, well, maybe, okay, I'll put that in a minute. Okay, that's because I want to make sure that I formulate that question in a good way. So I think the point here is that you can start from any node and find the shortest path to any other node. Okay. And the shortest path, again, I think the point I wanted to make was that the shortest path tree is going to be different. Okay, so the shortest path tree, if you start with I as the root and find all the edges to other things that lead to the shortest path to all the other edges, that's going to be different from when you do another node, obviously. Okay, so that's one of the points I want to make. Another algorithm is finding strong components. Again, I'm going to leave this to you to kind of think about. I think in this graph, you can see that there are 1, 2, 3, 4, 5 strong components. What we mean by a strong component is that if you start from any node, this is a directed graph. If you start from any node, you can reach every other node in that unit. I think something very similar you did with the program for finding clicks, for instance. Okay, with that's with an undirected graph you were working on. But I'm going to show you a good algorithm for finding strong components. Okay, this algorithm is called Kosaraju Algorithm. In fact, the story is that the professor forgot the notes and of how to find strong components of an algorithm that existed, and then he kind of made up something, and it turned out to be better than the algorithm that was there. So the Kosaraju was the professor. But here's the algorithm, and I will make a video to show you this because since we don't have time to run this thing right now. And GR here is the reverse of the graph. Okay, GR is the reverse of the graph. The reverse of the graph, you find the reverse of the graph by reversing the edges. Okay, you might think about why this works. For example, the reverse of the graph would be like this. Okay, all those red arrows that I draw are reverse arrows. So I'm drawing these reverse arrows, so I can draw many of those. Okay, so the algorithm says you run the reverse graph, which is the reverse of G, which is easy to do. All you have to do is just reverse the edges. If you have edge 1, 2, make it 2, 1. Okay, and you compute the reverse post order. You compute the reverse post order. Okay, for as an example, post order means that you do DFS. So you essentially do DFS, and you find the post order like we did with the topological sort. If you recall the topological sort, that's where we did the reverse post order. Okay, so let's assume that in the reverse post order you came up with a set of an ordering. Okay, something like this, maybe something like that, right? And then it says you run the DFS on the graph itself, not on the reverse graph. G is the graph, considering vertices in the order given by the first DFS. In other words, you start with 6 and you run DFS, and you would assume that your DFS will only produce 6 and 8, because 6 and 8 are in a strong component. Okay, and obviously 8 is now not considered because we don't have to worry about it. And then you take 7 and run DFS, but according to this graph, the 7 can only produce it would in the, I think if you do the DFS in the graph, you will find out that one second, yeah, it will end up with the run the DFS considered given order by the first DFS. Okay, so actually this is not the right. I just made up this example of the reverse thing, so that's why it might not make a lot of sense right now. But if you actually do this, and I will do this as a video, and this is a very easy algorithm for finding strong components. Okay, it deals with the reverse graph and the reverse post order, and then run the DFS on G. Okay, so so I will do that as a small video and leave it there for you to watch. Any questions there about this? In fact, you might want to try this before I make the video, just to see if you can get this. Okay, if you can figure out the figure this out. Okay. All right. Now let me just do 10 minutes left. So here's our course summary. What we learn in this course are data structures like linked lists, binary trees, BSTs, AVL trees, graphs, heaps, priority queues, stacks queues, and hash tables. And there are other data structures that we didn't learn and that are also very practical things, but they were not part of this course. We also learned algorithms because different data structures need different types of algorithms to process the data in the data structure. And then more importantly, in this class, we did a lot of analysis of time and space complexity. The reason we did that is the reason is that the analysis of algorithms, which you might take at some point, help us scale. Okay, that's the big word here. Because as n goes up, we know that even n squared is very, very slow. And we like something in the order of log n, n or n log n, the worst case. And because we are dealing with large amounts of data, which are in millions of records. Okay, and the data structures is the key building block of the abstract data types that you build in your program. So you try to abstract away the requirements and you build data structures. To process the data, they have to be stored in the appropriate data structure. Okay, so we put them in the memory, but we create this abstract data type, data structure to store them. And the proper data structure is chosen based on the application needs. So how you choose a data structure based on what the application you're going to be working on. Okay, and the algorithms act on data structures to process the data efficiently. Okay, here are some interview questions for you. A few minutes left here. We need to find the second largest element in a BST. How would you do that? So it's an algorithm for finding the second largest element. Very good. I think that's correct. So given a binary search tree, go as far right as you can go. And that's going to be the max, but the parent is the second largest. Yeah, there are special cases such as trees null or things like that. But we know that the parent, if you find the last node all the way to the right, the parent of that node has to be the second largest element. Okay, we need to store billions of pictures and find them quickly. What data structure would you use? It is a hash table. All right. So hash table, sorry, there were some questions here. Would not be the left child. Left child is not, because left child is smaller than the root, right? Yeah. So hash table, even if you have billion things, and you can store billion pictures in linear time, because each one will take big O of 1 for a hash table. And then you can find them in big O of 1, any one of them in big O of 1. So to store something in a hash table is big O of n. To find it is big O of 1. Find anything. So the only reason you don't use hash table, then you might say, why don't we use hash table for everything? Why don't we use hash tables for everything? Anyone knows the answer to that question? They are not ordered. Okay, so hash table are not ordered. So if you put anything in a hash table, you cannot do any order operations like find max, find mins, and other things. Okay. This question, the third one, is kind of difficult. It says, design a data structure that can find median in big O of 1 and insert an element in log of n. In fact, this is done by designing a data structure like this, where the left-hand side is a max heap and the right-hand side is a min heap. And it turns out that the root, or something close to the root, would be the median. And we keep everything less than or equal to the root to the left, everything more than or equal to the root to the right. Okay, so you can design a data structure that can find median in constant time and also maintain the data structure by inserting any element in log n time, because in this case you just have to keep an almost balanced things in there. Fourth question, we need to sort 1 million middle school students by their age. How can you do that? Yeah, so there's a sort, obviously you don't want to do any kind of a sorting algorithm you already know, like quick sort or anything like that, because they compare elements with each other. At some point, you can actually do research and find out that this can be done, what's called a radix sort, or a simple idea called bucket sort. Okay, so it's a bucket sort. The idea would be that you have a bunch of buckets and the, say, middle school students are 12, 13, 14, 15, maybe not. Okay, and you have n of those people and you put them into buckets. Okay, and that can be done in linear time. So the sorting can be done in linear time because all you have to do is to look at the age constant time, and then you put to the right bucket, and there are a finite number of buckets in there. So what's the best way to find a strongly connected component in a graph, which I showed you? That algorithm, I didn't show you how to do it, but hopefully I'll do it with a video. Okay. So this brings us to the end of the course. This is as far as, so what are the next things in the curriculum? So there will be a lot of theory courses like discrete structures and other kinds of formal languages and other kinds of theory compilers. There are a lot of application courses in the curriculum. The systems courses deal with mostly in C language, deals with very low level ideas. Now here in data structures and algorithms, we dealt with very higher level. We didn't look at the memory, we didn't look at the bits and bytes, but in systems courses, you're going to be dealing with those things. And in AI courses, obviously, a lot of interesting in AI courses and deep learning and artificial intelligence. And data science courses actually combine working with a lot large data sets that people are looking to find patterns in data sets. Okay, so computer science as a field is very promising, so I encourage you to stick with it, although it's very hard and it's very time consuming. But as a field, it has a very promising future, and you have to learn as much as possible there. Okay, so computer science is an exciting field. I wish I could have been there in person to tell you how excited I am to be a computer scientist. I think my life is not boring. I mean, it's busy, but not boring. Okay, so I think I will take that for any time for not boring and boring and not busy life. So I'll be busy and not boring than the other way. Okay, with that, I want to say thank you for taking the class. And I only saw you guys maybe 6 weeks, something like that. And I wish you well. And hopefully that you all do very well. And hopefully I'll see some of you in my classes in the future. My semester, very good. Thank you for your notes here. I enjoy reading them. Whatever comments you have is appreciated. My semester was kind of boring, the second half, which I wish it would have been different, but I hope you were able to learn something from here, and it's not perfect conditions, but we did the best we can, I guess. And that's life. We have to adjust to whatever comes our way. Thank you very much for taking the class. I'm glad to hear that you adapted well to the virtual setting. I know I did okay after some struggle the first class, but it was, I think it went okay, but it's, I never really learned how to teach online. Yeah, so I think everyone worked hard. I think a lot of students really had to struggle, I know, to kind of keep up with the course. And so hopefully we'll meet, we'll be back on campus in fall. I'm not sure yet. If you do, just stop by and say hello. Or maybe I'll see you in a future class. Okay, so some Sean seems to be, yeah. If you're ready, if you want to take discrete structures, I know my sections are closed right now, but if anyone who took class with me, 112, I will be happy to let you in. You just have to apply for an SPN. The discrete structures is a very different kind of a, there are no programming assignments, so it's much more mathematics. It's all mathematics. And the difficulty is in the sort of understanding how to prove things. But it's a fun course. I really enjoy teaching that class. There's zero programming assignments in discrete structures. It's all logic and proof techniques and other kinds of things. I do not know difference between Math 200 and discrete one. As you know, I'm still new at Rutgers, so I don't know either if you can replace discrete one requirement with Math 300. I'm not sure. I know some engineering departments also teach some kind of a discrete class. In the past, some people have come to take the computer science version of it, which is, I think, much better. I teach discrete structures. I don't teach discrete structures too. I have not done it. I might do it in the future, but not right now.